what do you call this again? Oh, surface integrals. So we need a surface, right, if we're going to integrate over a surface. So let's draw our surface. My surface is usually drawn in black. And then we want a piece of the surface, so we can think about having a region here. Square regions are usually nice, but it doesn't have to be square. So I'll put another random region, call it D or R. I think we call it R or D. Let's call it D. And I was kind of fixated on a point here. Call it AB or X naught, Y naught. Let's call it AB. So then I have a point up on the surface that's AB. What's my Z component again? So now you're leaving. So AB, F of AB, that's your Z component, right? And I think last time we were talking about partitioning this up. And then, very small here, would be two vectors. I'll try to draw it, one in red and one in blue. That would correspond to tangent vectors. Up in space. Okay. Now, if we vaguely remember our information, I think we'll call the red vector going along the y-axis, so I think we'll call this one delta y. And then the blue vector going along the x-axis. Oh, it looks like it's going in the wrong direction. I want it to go this way. So positive direction, sorry. In the positive x direction this way. And we'll call this one delta x. Okay. Now, if you remember the specific values of these are the vectors that are on the plane. But I was kind of interested in finding the vectors up on the actual surface, the tangent vectors. So if you remember what those tangent vectors were, they had something to do with the partials with respect to x and with respect to y. Remember that? So let's label these vectors in space now. I'm going to take this blue vector and try to analyze it and see what's going on. It looks like I'm going a delta x in the x direction, and I'm not moving along the y direction, so that looks like it's going to be 0 in the y direction. And then I am moving along the direction of my slope, so in the x direction, so fx delta x would probably be my z direction. That's my up and down motion. So let's call this Vx for the tangent vector along the x direction, and then the Vy business goes along the x and 0 direction, because it goes all in the y direction by delta y, and then I have Fy delta y. So this is kind of where we left off last time, and I was talking about having two vectors up in space like this, and then I said there's one thing that we really wanted to do with this, and the one thing we wanted to do with this is cross it, and by crossing it we're going to get two important values. What happens when we do cross this? What are we going to get? A what? A normal vector. Okay, and then the other piece of important information that we'll need is the area of the parallelogram. So you take the magnitude of the cross product, you're going to get the area. And so we're going to move towards this idea of a surface area. All right, so if we cross it, and what I want to do is I want to cross it in a particular way, in a particular order. I want to cross the first independent variable, which is x, and then the second independent variable, which is y. So I'm going to cross the x first. So Vx cross Vy. If you do the cross product, the first one looks like it's going to be negative Fx and the second one looks like it's going to be minus Fy. And then the third one looks like it's going to be delta x, delta y. So this is going to give us a direction, and if we take the magnitude of this, well, we could take out the negative. We could take out a delta x, delta y scalar. And since they're distances, we actually don't need the absolute value around them because they're going to be positive anyways. And then we just need the magnitude of the vector negative Fx, negative Fy, and positive 1. So I didn't draw the, I wanted to draw the normal vector. I have two options for my normal vector. I can either go outward or inward. Which way is my normal vector according to this cross product? Which way is it going? Up or down? Positive 1, so it goes up. So it goes up like this. So this is perpendicular to both of these vectors, and that's positive. So the direction of your normal vector gives you the orientation of your parameterization. Yeah? Yes, it is a square. The squares added together. So let's go back to this business. So delta x, delta y, and then fx squared plus fy squared plus 1. So I don't know if you guys remember the negative 1, where the negative 1 comes from, or positive 1, where the positive 1 comes from. The gradient, if you remember, the gradient is perpendicular to a level curve, and it's perpendicular to, it's perpendicular to a level curve. When you have a function of two variables, it's perpendicular to a two-dimensional level curve, and your gradient's two-dimensional. And then we've often talked about making this gradient, not the gradient, but finding a vector that's perpendicular to a surface, right? So the gradient would be down here on the xy plane, but to make this vector over here, you need to add or throw in a negative 1. So if your fx and fy were your gradient, positive, then a perpendicular vector would be throwing a negative 1 in for the z component. But you can also have another vector that's perpendicular that's going the opposite way, where you have a negative fx and negative fy, and then now your third component is positive 1. So there's a positive 1 that comes out. Okay? So look at your last exam, problem number 2. When I asked for the normal line, you're looking for a vector that's perpendicular to the surface. And the surface was described as z is equal to f of xy, so it's a function of two variables. If you put the gradient there, that was incorrect because that's a two-dimensional vector. I want a three-dimensional vector because this is happening in space. The normal line is happening in space. Okay. So this business looks like it gives us a surface area. Surface area of what? It looks like it gives us the surface area of a small piece of that surface that we're looking at. Right? So now imagine if we're just double integrating over this domain D, then that would give us the rest of these little square pieces that we can add up. And so we can have the surface area of a surface, the area of a surface using a double integral. So here's the formula that comes up. So area of surface z is equal to f of xy over the domain D is going to be equal to a double integral of fx squared plus fy squared plus 1 dA over your domain D. Yeah?
Isn't that also like just adding up a bunch of arc lengths over another variable? And then you just like have the curve by adding another variable in it?
More or less. But that is a good thing to look at, the arc length business. So let's do a little recall box here. The arc length looked like this, right? It was, how did it look like? So it looks very familiar, right? So what's this got to do with parameterizing? Well, the way we found our domain was we used this thing called graph parameterization, where you have x is equal to x, y is equal to y, and z is equal to whatever that is. So this is a specific kind of parameterization that I would call the graph parameterization. But it turns out that we can get a little bit more complicated if we wanted a more complicated setup of a surface. So let's talk about finding the surface area. I wonder, I'm going to have to derive everything over again. Let's see if we can do it quickly. So I think I was using a capital phi last time, right? So let's say we have another parameterization that's not a regular standard parameterization. Where we have the u and the v and some domain d in here that gets mapped into some surface in 3 dimensions. Okay? So this could be this parameterization right here. And then the domain would be this. Right? Do you remember what this thing drew out for us? Or half of the sphere, right? So we can do the same ideas, play the same games, where we would find a couple of vectors. If you partition this D, if you partition this D, you would have the same sort of ideas over here. So these vectors may not be perpendicular. It was perpendicular when it was in D, but then when you brought it out here, it might not have been so perpendicular anymore. And then what you could do is you can find the area of this thing, or take the cross product of those two vectors and find the same area over here. So what you have here is a transformation that takes 2 variables to 3 variables. And when you do this transformation that takes 2 variables to 3 variables, this first vector over here, the red vector, would be that transformation in the direction of u. And then the blue vector would be that transformation, the derivative of that transformation in the direction of v. So we'll do the same business where we take the cross product of that. So I don't know what they are anymore because I don't know what the transformation is. I mean, if we actually work out a problem, then we'll figure it out. But we don't know what that is yet. But we can cross it to find that area. Well, first of all, we can cross it to find the cross product, to find the normal vector. Whether it be going up or down, I don't know. But if we're finding the area, that doesn't really matter anyways. We'll just find the area. So the area of this thing is the magnitude of the cross product of those two things. Okay? And so when that happens, it becomes, you tack on the dx dy business, which is, in this case, the delta u delta v. But I'll write it as du dv, but you can switch the order if you need to. Okay? So then the area of this thing is going to equal to a double integral over d of the magnitude of the parameterizations du dv. Okay? We're probably really eager to see an example, so let's do a quick example. What previous formula? Oh, that one was just related to this. But we will do more relating in a minute. Yeah, this is square root. This is, what do you mean, this one? Yeah. Yeah. Yes. So are you talking about this relationship between the, oh, okay, you're talking about this. Yeah, so just like Ryan said, it's the magnitude. So this is a cross product. If we know the parameterization to be this graph parameterization, where you're using essentially the same variables for x and y, or x and z in this case, then your cross product is equal to this. But in more general cases, you don't know how it's going to look like, so you'll use this. All right. So let's do an example. And your hemisphere let's say is this parameterization that we have here. Your x is equal to 2 sine phi cosine theta. Your y, we switched it, is equal to 2 cosine phi, and your z is equal to 2 sine phi sine theta. So this is your parameterization. Your domain D is given by the limits 0 phi to pi over 2, 0 theta to 2 pi. By the way, before we work this out and get an answer, what should this equal? What should the area be of a hemisphere radius, of sphere radius to? You guys remember the surface area formula? The 4/3 is the volume. What? No? Well, did you work it out already? Okay. What's the area of a sphere?
4 pi r squared. It's either 4/3 pi r squared or 4 pi r squared. It's one of them.
4 pi r squared. The 4/3 is the volume.
And it's 2 pi r squared.
So and r is equal to 2 in this case. So our answer should be 8 pi. Okay? So let's keep that off to the side here, and let's actually work it out the way we're looking at this transformation. So this is supposed to be your phi. When I say phi, capital Phi, it's your transformation phi. And then we have phi of phi. And we're going to need phi of little phi, and then we need phi of theta. Those are our two independent variables. So let's figure out what phi of little phi is equal to. So along my x, y, and z, if I take the derivative with respect to phi, the derivative of sine is cosine positive, so this would be 2 cosine phi cosine theta. The derivative of the second one with respect to phi, this is cosine phi, that's negative sine phi, and then there's a 2 there. And then another sine, so that's the same business over here, positive 2 cosine phi sine theta. So that's the first one. I'm going to get my Mathematica ready because I'm not going to want to cross it and then take the square root business, which is what we'll need to do. So the next thing is to find capital Phi of theta, the derivative of this thing with respect to theta. So this is a cosine theta, so that would be a negative 2 sine phi sine theta. My y component is 0 because there's no thetas in there, and my z component is going to be a positive 2 sine phi cosine theta. Now this is the part that I don't want to cross. So I'm going to let Mathematica do it for me. Maybe it's just cross. I have 2 cosine phi cosine theta minus 2 sine phi 2 cosine phi sine theta. So that's one vector. The second vector is minus 2 sine phi sine theta, 0, and then 2 sine phi cosine theta. 2. Okay. Wow. So it looks like it could simplify a little bit to this thing. And now we want to take the magnitude of that. Oh, now we want to take the magnitude of that. Should have kept this. So the way I do magnitude here is I don't think they have a function called magnitude, but I can just take the dot product and take the square root, because that's the same thing as magnitude. So that's what I'll do. Square root of the dot product of the last two outputs. Which is equal to this. Yeah, so mathematics is careful not to take the squares out of the square roots, because unless you tell it to, because it has some issues with the square root function and imaginary numbers. So let's see if we can actually do it ourselves here. Unless I can have it simplify. Let me see if mathematical will simplify. Oh, there it goes. Sorry for making a mess here. Aha. There he goes. So this is what I ended up with. The cross product. So this is the cross product, or the magnitude of the cross product. Yeah. So it's just 4 sine phi. Okay. So let's finish this off with finding our area. Area is equal to the double integral over d of 4 sine phi d phi d theta in whatever convenient order we want it to be. And if you remember our d, our phi went from 0 to pi over 2, and our theta went from 0 to 2 pi. And so there's the 2 pi is, what do you call it? Constant. So this integral here, what's the antiderivative of sine? Negative cosine of phi from 0 to pi over 2. Cosine of pi over 2, 0. And cosine of 0, 1. So it's a negative negative, so that's just left with a 4, right? So you have integral from 0 to 2 pi of 4. I suppose we could have split this up, but this is just going to be 2 pi times 4, 8 pi. Okay? Is that cool? All right. Let's see if we can extend this a little bit more. Because this is, now that it's become a formula, it's not that big of a deal, right? And we're just finding the surface area. Now let's do a comparison from when we were doing arc length. So when we're dealing with arc length, we parameterized it using R. And then we gave it some limits for your interval A to B. So this isn't the regular, that first example where we wanted to compare how we did it with the my recall little box over here. This is for arc length of y is equal to f of x function, right? But then we can parameterize this for using any parameterization R now. Where the arc length L is equal to the integral from A to B of the magnitude of R prime dt. Do you remember that? Okay, we did something else to this. Well, we'll take a look at this in a minute. But now the equivalent business here is that we have a parameterization phi of u and v, and then the uv is going to be part of a domain D. And so now we found that the surface area is equal to a double integral over D of a magnitude of some sort of derivative, but the derivative is a little bit more complicated because we have two variables, and so what they came up with is this idea of taking the derivative with respect to one variable and then another variable and then crossing it. du dv. Okay, so I want to say that these two things are equivalent. They're kind of saying the same thing, except one is dealing with a curve in a one-dimensional object, and then the second one is dealing with a surface, which is a two-dimensional object. Okay so far? Now, do you remember back when we said we're going to parameterize by arc length? And then we decided to call this ds. Yeah? Well, we can say the same thing here. We can parameterize by the surface. Actually, let me change the notation for the arc length one. And I think we eventually moved to calling this a C for the curve that R has parameterized. So here, that's where we're going to move towards. Now this whole expression over here will be our ds, parameterizing, and we're integrating over the surface. Okay? We're integrating over a surface, and so we need to parameterize over a surface. So now, there's a little bit more here. We had this notation where we say we can integrate over arc length. And then we decided, oh, what if we can just integrate something in here over arc length? So we had one of these jobs where we took this integral and then we put a scalar function in here. Remember what this is called? What? No. What is this integral called? It's called the path integral. Remember that? Well, now there's a new equivalent, a new kid in town, so to speak. Guess what this is called? Surface integral. Okay. So geometrically, this is hard to visualize because the idea of integrating a function over a surface means you have a two-dimensional thing in 3 dimensions, and then you're integrating another three-dimensional function f out of there. So trying to visualize that and trying to get some idea of what that might look like geometrically is kind of difficult. But an application for a surface integral is like finding a mass of a surface. So if you have a sphere that has a density that's dependent on some x, y, and z, you can find the density of that surface. So we can do that as a quick example. So application of a surface integral would be let rho, we use rho for density, right, or delta? Rho equals, let's try to keep it simple, k times z. And we could put units here, whatever the units are, kilograms per meters squared or something. B, the density of a surface. Let's make it a cone. And here we start describing how we want our cone set up. So maybe we want to say the cone has a height of 3 or something. So the cone goes from 0 to 3. You can ask to find a mass. So this is your cone, and you want to find the mass of this cone depending on this density business. So what we can do is parameterize the cone and integrate over this thing. So the mass, arrow, the mass is going to equal to the surface integral of this density function over that surface, right? And there's a couple ways we can do this depending on our parameterization. So we have a choice in our parameterization. We can stick with the x's and y's. And if we stick with the x's and y's, our drawback, I think sticking with the x's and y's is easy, but the drawback is that your domain is going to be a circle. or we can go into cylindrical right away. But either way, we'll see that we're going to come up with the same result. Not only the same result, but either way when we do our transformation, because when our domain's a circle, we're probably going to want to go into polar when we integrate. So the question is, go to polar now or later? Okay? All right, we can go, let's go later. And then maybe you guys can go to polar earlier if you want. So why don't I keep the same parameterization here for x and y. So the parameterization that I'll choose is x is equal to x. I can use u's and v's, by the way, or u. Y is equal to y, or v. And z is equal to the equation given to you, or u squared plus v squared. So I'm going to stick with x's and y's just to keep it as graph parameterization. So I would need the derivatives of these things. Actually, if it's a graph parameterization, we already know the ds, right? ds is equal to the square root of, well, I still need to find those. This is my surface, f of xy. So fx is equal to the derivative of this thing with respect to x. So it's x squared plus y squared raised to the negative 1/2 power. And so I'll put that in the denominator times the derivative of that is 2x. The derivative of the inside is 2x. Okay? So fy is going to be 2y divided by square root of x squared plus y squared. And then z, well, there's no fz. So I would cross them, and then I would get that square root of fx plus square root of fx squared fy squared plus 1. So ds is equal to the square root of fx squared plus fy squared plus 1. So this thing squared would be 4x squared over x squared plus y squared plus 4y squared over x squared plus y squared, and then 1. Okay, so I'll probably want common denominators. It looks like the common denominator is x squared plus y squared. So I'll have 4x squared plus 4y squared plus x squared plus y squared. So that's going to give me 5. And then if you factor a 5 from the numerator, you're going to x squared plus y squared on top and the bottom that are going to cancel. So your differential is just square root of 5. I forgot my dx dy here. Okay. So then that's my ds. The ds came from here. And then now I just need to replace my z with x squared and y squared. I would replace it with whatever the independent variable is. So back to the mass here. K times z, which is square root of x squared plus y squared, times 5 dx dy. And remember that my domain here is a circle. How big is my circle for my domain? You know what the radius is? What? It goes all the way up to 3 here in the z, which is the same as the x squared plus y squared business, so it's just going to go from 0 to 3. So now I can go to polar coordinates. And my polar coordinates will have my r go from 0 to 3, and then my theta goes all the way around 0 to 2 pi. So my integrand here, yeah. Okay. So you can finish this. All right. So yeah, it just goes from 0 to 3, k, r, 5, and then now the r, dr, d theta. Because I forgot. Yeah. So this is your integrand, which is easy enough to integrate. So that's the mass. Okay, so that's surface integrals, and then we're going to go over one more type of integral, and that will complete our list of kinds of integrals for the rest of the semester. And then we'll just play around with switching them, whatever that means.